Hello, I would like to introduce my research topic analyzing excess spectra of ruthenium complexes using the machine learning approaches. And my work is aimed to developing of machine learning approaches for the analysis of ruthenium XANES spectrum as well as study of the evolution of ruthenium catalyst. And there is an interesting catalytic system consisting of ruthenium salt dissolved in ionic liquid, which is rich of brom atoms. And it is interesting because the ruthenium catalysts have a promising application in the reaction of hydrodeoxygenation of sugar alcohols to alkenes, which are essentially the building blocks of the modern chemical industry. But unfortunately, this reaction can further lead to the hydrogenation of alkenes into less variable for us alkanes. And the ionic liquid tetrabutylphosphonium bromide helps us to avoid this transition. This catalyst system was studied using PTIR and XAS spectroscopy in the joint project with our colleagues from Leuven. And XAS in principle give useful information. For example, in this work it was already demonstrated that the working catalyst wasn't pure ruthenium bromide salt, but carbonyl bromide ruthenium. And these interesting results motivated us to track the evolution of ruthenium species in the working catalyst in more detail. But it became a complicated task due to the very low concentration of the ruthenium, especially in the operando mode. So the classical XAS data and analysis was limited, especially in the EXAFS region, but it's less critical for XANES. And in turn, to take a quantitative information of XANES, XANES analysis require some more methods. For example, we use the machine learning approaches. And to further studies this catalyst system and determine the two catalysts, we conducted two experiments. The studied samples were in some kind of frozen states with a high concentration of ruthenium, and in frozen states with a real concentration of ruthenium. Ruthenium salts was with chlorine and bromine was taken as a references sample. Based on the coordination number and distances obtained from the references sample and extensive DFT calculations, we proposed several structures and used them to the further XANES simulation. Then we have chosen different deformation that of this molecule that will have the strongest impact on XANES. And in total, there were 5 different deformations that you can see on the slide. And to train the machine learning algorithm to predict 5 structural parameters, we have to use a very big training set. So we performed more than 3,000 ab initio calculations. It was a theoretical calculations spectrum to make this training set library. And on this slide you can see the results of comparing the data analysis of EXAFS and XANES with using the machine learning. And as you can see, the data is in a very good agreement. Yeah. So, and as a conclusion for this part, I would like to highlight that we constructed the theoretical XANES training sets for spectra of ruthenium-based catalyst, and now we can accurately predict both like structure and the ligands surrounding of ruthenium from XANES. Okay, let's move on to the second part of this study, and we want to track the evolution of ruthenium species in the working catalyst. And for this part, we will possible use not only XANES spectra but also performed EXAFS analysis and complement it with DFT calculations. And in the first step, we investigated the role of ionic liquid and the XANES and active spectrum of the initial ruthenium salt, its dashed lines, and those which was dissolved in ionic liquid, its solid line shown here. And as you can see, there are no shift in the H position. That means that there are no change in the oxidation state of ruthenium. Also, for ruthenium bromide compound, the ruthenium bromide coordination number decreased from 6 to 4, and for ruthenium fluorine compound, a significant reshaping of both EXAFS and XANES data is observed, which is associated to the chloride and bromide exchange in a reach of ionic liquid of bromide. And we can say that we form the tetrahedral complexes for ruthenium bromide salt in ionic liquid, and DFT calculation also confirm this information. And on the next step, we add CO, and XANES spectra give clear indication relative changes in the number of CO and bromide ligands. In particular, both PCA analysis and DFT calculation show that after reaction of CO ligands is replaced by bromide ligands, and that means that we form the ruthenium carbonyl bromide species. Next, we want to see the role of ionic liquid, but we start with ruthenium carbonyl species with chlorine or bromide. And as in the previous case, in the first case, we see the strongest change in the spectrum observed for chlorine containing precursors, which is also associated with the chlorine-bromide exchange. And secondly, being dissolved in ionic liquid, both precursors exhibit increasing in ruthenium bromide and decreasing in ruthenium CO contributions. And this fact was supported by DT calculation, which demonstrated that the transition shown on the slide is energetically favorable. And as a result, summarized in the following scheme for the evolution of ruthenium catalyst. And as a conclusion on this part, I would like to know that in ionic liquid rich of bromine, the chlorine ligands are replaced by bromine, and when CO is added, ruthenium carbonyl is formed. And this slide shown all the conclusions that I mentioned before. I would like to know that there are many plans for the future. For example, publish 2 papers about the machine learning and chemistry part of this study. Also, we want to apply a new approach implemented in PyFitIt that I used to analyze the XANES spectra with using machine learning, and it would be called the descriptional analysis, and it can allow us predict ligand surrounding based on the spectral features. And also we want to calculate intermediate states and reaction barriers for our catalyst. And in more details, research the transition states of our ruthenium-based catalyst. Also, we want to conduct an apparent experiment at the solely synchrotron to study our catalytic system. I want to thank you for your attention and my colleagues who work with me on this project.